Okay, I'm going to go ahead and get started here. I posted last week that midterm example, right? So everyone's had a chance to look at that. Any serious questions? I'm not going to do it for you, obviously. It's that there, but so keep in mind that today's lecture is to try to fill in some gaps that might have been on that there. So I'm going to use today's lecture because there's a few new points in it that was not covered previously. So what's covered today will also be open game for Thursday and the final exam. I'm stealing some slides again, as I normally, from Dr. Ashish Gupta. He's a mechanical engineering. And keep in mind that the subject of robotics and industrial automation at a lot of universities finds itself more in the manufacturing and mechanical engineering departments. I taught industrial automation in the mechanical engineering department back at my old campus. So, okay, there's several subsystems. This is just an example. Again, we've gone through that there. The controller, and right there. There's our controller. That's usually our microprocessor. We have our motor of some type. We'll talk about those. What we're going to be looking at here is that this is actually an optical encoder. That's one of the sensors that we'll talk about here. And then this is the actual robot that's being moved back and forth right there. And we have a feedback path right there. So this is a typical system right here where we've got a controller, actuator, sensor, and the process model right there. So again, this slide is very simple right there. So, and I think I've gone through some of these slides, so some of these are repeats, I know, but this is an open loop system, a closed loop system. So be sure you know the difference between the two, an open loop and a closed loop right here. And right there. And there's a required course in feedback control systems. Robotic control definitely falls under the area of feedback control right there. So here we have our process. Our output variable comes from the sensor. I'm going to just concentrate predominantly on the various sensors that there. Our input parameter usually comes from some control aspect that we have that there. It can be a keypad. It can be a program that runs the controller. Typically when we look at a production line, we have some kind of software control. So these are the basic elements that you need to be aware of. Sensors, actuators, controllers. In the system model, we won't get into the system model right there. So we talked about actuators earlier. I pointed out the three types of actuators. The pneumatic, hydraulic, and electrical, and types of that there. The controller, we've talked about that. That's the microprocessor. It can be a computer, or it can be a microprocessor board. It could be some type of analog controller. Those aren't common anymore. Back in my early days, when I first started school, this is actually by the time I finished school, they were already obsolete. We used to have what they call an analog computer. And analog computers were used for feedback control systems, and there was predominantly analog calculations going on, and you would solve differential equations and integration using analog circuits, predominantly 741 op amps in some type in that there. Those aren't used very often. And we're not going to get into the math of the system model right there. But I'm going to just go through all these slides today. There's basically two general classes of sensors. The internal for basic working in the system, velocity, position, and then you also have externals that are going to be looking at. Internal is telling you what the robot is doing, or the car is doing, or the up there. External is what is happening on the outside world. You know, is is somebody pressing a button? Is there a certain amount of light coming in? Is there, an object in front that we can see? How far are we from a particular object right there? So that's the external. So you've got two types. When we look at position, velocity, and acceleration, those two are typically internal. What is the vehicle or robot arm doing? External is what's around there. Is there a box for this robot arm to pick up? Right there. And that would be a vision system or a proximity sensor or an on-light sensor of some type. Right there. You would have a sensor that would sense the outside world. Right there. So closed loop internal, these are the three that we normally would use. And as I said, that their position is where is the robot in position, with respect to its world. And our robots do not have any sensors. The ones that you did the lab with, there's no sensors on those robots right there. Velocity is how fast the robot is moving. Now, if we're talking something like a remote or a self-driving car, the velocity is very important right there. And acceleration. Acceleration, of course, is the velocity with time. In other words, how fast is our velocity changing right there. So, and actually, velocity is dx dt. That's change in position. So these are all, and this is x. So you can see where we could write differential equations to solve these using these various that there. So this is also equal to dx squared. Right there. The second derivative with position is acceleration. Right there. So when we're looking at internal sensors, we're looking at the position of the robot or system. We're looking at how fast it's moving, and we're looking at how quickly the speed is changing or the velocity is changing right there. So, and all three of these can be measured. A potentiometer can be used to measure a position of a robot arm. An encoder can be used to measure the position of a robot arm. And now the position could be converted to velocity or acceleration in software. That there. LVDT is a linear voltage differential transducer. That's typically an inductor of some type. A tachometer is a way of measuring velocity. On a wheel, we count how many pulses we get, and that can be converted to speed. Right there. An accelerometer is a special sensor that measures change in speed. Right there. Now, if you're looking at something like an aircraft, an accelerometer is probably more important than if you're looking at a robot arm on a factory floor or the moving of an assembly line on a factory floor. There, you rarely would look at the acceleration. In a car, you might look at the acceleration. You may want to keep the acceleration below a certain point. You don't want to go from 0 to 100 kilometers per hour in 0.5 seconds right there. You might push a few people back in their seats and cause the driver to lose control right there. So again, we're looking at the, but you need to know what these three types of sensors are and what they measure. And again, you need to come up with examples where they would be used. When I say an example, I don't want to know the type of sensor. I want to know when I ask for an acceleration that explain what an acceleration sensor is. That there, and you would say it measures a change in velocity, blah blah. That there over a period of time, and give an example where one might be used. And then you might look at, say, for example, an aircraft engine, or aircraft controller, because you're looking at how fast you're descending right there. things like that. Or how fast your speed is, you're accelerating with your car going down a hill or going up a hill. Velocity is fairly easy. What is the speed of the arm? And remember that the speed of a robot arm, you have to control that. Because if you go too fast, you can't stop it. And stopping is a form of acceleration, right? It's deceleration. So stopping something is a type of acceleration. And quite often, we have to control the rate in which we stop a vehicle. If we're looking at a self-driving car, we can't stop it instantaneously. That's how seatbelt passengers fly through the windshield. We have to control the rate of deceleration. That is something that has to be controlled when we're looking at a vehicle or a robotic arm, is the rate of acceleration. So quite often we have to measure it. Right there. These are some external. Right there, this is a pretty good list. Right there, that's why I went to switch slides from last time. And I don't think I did put these slides up before class because I just downloaded them to talk about it. Touch, when you think of a touch, you're talking like your cell phone, you touch the front, that's a touch sensor. Force is how much you place on that. A good example of a force sensor in operation might be your bathroom scale. You step on it and it says that you weigh 90 kg. So it's measuring the force on the scale right there. So pressure is, you look at the amount of hydraulic fluid, so you have a pressure measure. But you also may be looking at other things. There's a fine line between pressure and force transducers right there. So, and I'm going to use the word transducer interchangeably with sensor. They're the same thing. Slip is one I haven't talked about, but slip is, you've got a rotating object and then it's driving another rotating object and they're not keeping up with each other. There's a little bit of slippage there. I have never used a slip sensor, but they do exist. Proximity I've used a lot. They say whether or not you're close to a particular object right there. So an example is, here's an assembly line, here's a line, and you use an assembly sensor to sense whether or not a box is in a particular position, right? Then you may have a vision sensor to look at the box and look at the barcode to decide where this box goes. Now I've used vision sensors for all kinds of objects there. So, and then of course there's other types of external sensors, light sensors. I mentioned the potato sorting there, where we shine a light of a certain color and we measure how much reflected light is coming back. And that tells us how much green is in the potato. Certain lights, there's certain colors and material will reflect different colors differently or absorb different colors differently. So by using LEDs, we can shine red, yellow, green, and we can measure the reflected light coming back and determine whether or not there's black spots or green spots on a potato chip. And then we can use a puff of air to eject it and say that it's no good anymore. So here, on-off switches are that they're ultrasonic, force, Hall effect. These are all, Hall effect is typically a proximity sensor. An inductive sensor is typically a position sensor right there. Piezo. Oh, here we go. Here's a potentiometer. Again, what we're measuring is location. So as this thing moves back and forth, it changes voltage on the wiper right there. So this is a position sensor. Probably the easiest type of position sensor you've got. and this is an encoder. Now an encoder, basically what you've got are little lights at there, and we can measure movement at there. This is not a really good example. Most common is the gray code encoders, with a little at there, but I'm not going to. This is the gray code encoder. This is the more common type of position control. Not used very often anymore. This used to be a very common type of way of measuring position. Now you either use a potentiometer or you just simply keep track of it with a stepper motor, how many steps you make, and you calibrate it so often. So velocity here, the easiest velocity is just a DC generator. Right there. You place a little wheel on it, and it keeps track, measures the voltage that it generates, and that will give you the velocity. That's the easiest type of an analog velocity. Another type is a series of pulses that come from either a Hall effect or a reflective. Right. Oh. When we look at, if we have a wheel, what's going on here with my pen, right there, and it's got slots in it right there, and we shine a light through it, and here's my sensor right there. And what's going on here is it closed it. That was interesting. I don't know why I did to close it, but my computer is doing some weird things today. Now it's coming back up right there. And it's taking its time coming back up. Okay. Here's our slots right there. And looking at it from this angle here, we shine a light. And it keeps closing, right? Yeah, maybe I give up and I draw here. Here's my slots right here. Here's my light, shine through here. Here's my sensor moving as a series of pulses right there. And by measuring the time between pulses right there, I can calculate what the speed is of the particular object. That, or for a particular period of time, I count how many pulses there are. 1, 2, 3, 4 pulses. That will give me a speed right there. But again, that's a type of velocity measurement. Those are at there. And we don't have to necessarily use an optical. We can place on a wheel a magnetic thing and a Hall effect transducer next to it, and that will also generate a series of pulses. And this will talk about the Hall effect here in a minute right there. But we can either use light through a slotted wheel, or we use the Hall effect. Most industrial applications are using the Hall effect simply because light in these wheels, right, that there, the amount of dirt that clogs up these windows sometimes gets to be, they have to be kept relatively clean. They manage to collect dust and fill up with dust right there. Okay, touch sensors, on-off switches, emitter, receiver pairs, right there. These are types of things that measure whether or not something's touching or right there. Here's a proximity. This is typically called a Hall effect, but I have a magnetic coil. I have magnet there, and then there's a little coil there that can measure the change of inductance that they're essentially right there. So, but this just simply tells whether or not it's very close to a piece of magnetic material. So as I said, I could put a piece of magnetic material on a wheel right there, or I could have teeth on a wheel. Put a Hall effects proximity sensor here, and I can generate pulses as the teeth go by. There's all types of ways, but the way that this works is, the key is this drawing right here. That we have a magnet, this is the container, this is the coil, and again, this right here is where it's looking for the magnetic. There it creates a change of inductance right there. Again, this is the Hall effect, and it's the same type of idea. We've got the magnetic, and we're placing the sensor in between. This is actually the type you would use more often with the, but we're looking for a change in the magnetic field is what we're looking for. This is a range. This is an ultrasonic. The concept is relatively simple. We send out a pulse right here. Here's our pulse. And we look at when the pulse returns. It's very similar to radar right there. Now the whole idea is that when we look at an ultrasonic sensor is that here's my, and I'm going to call this my sensor. Here's my object. We bounce this off, it comes back right there. There's a reflection of the ultrasonic sound. This takes a period of time right here. The time from here to here, right there. So we're looking at a time difference, and this measures the distance. So when we want to measure the distance between a robotic arm or a vehicle and the vehicle in front of it, we use an ultrasonic. Cameras use ultrasonic sensors a great deal for focusing. Back in the old days, you know, and when I say the old days, when I was your age, that there, and really up until the time I was about probably 40, if I had a nice camera and I wanted to take your picture, I would take my camera and I would turn the focusing ring to where you were clear. Right there. Now I take my camera out and I hit the button and it uses an ultrasonic sensor to focus on a particular object. Right there. It measures the distance. If you use a digital single lens reflex, they use an ultrasonic sensor to measure that there. But almost all cameras today use ultrasonic sensors for measurement. Same thing with robotic arms and measuring the distance from the arm to the object that's picking up. A self-driving car, the distance between you and the car in front of it. It also does calculations to see whether the car in front, whether the distance is changing. If the distance between you and the car is changing, that means either the car is stopping or you're accelerating. And you need to slow down and keep that distance the same. Most countries require between two vehicles a set distance on the expressway. I'm used to typically, and I don't know if this will let me work. It seems to just, if I hit the button once and wait, it might work. But here's car A, and here's car B. The distance between the two of these cars, right there, you would have an ultrasonic sensor that would measure that, and you would want to keep this fixed. You know, typically, the rule in the States we always learned was 2 car lengths plus 1 car length at there per 10 miles per hour. I mean, this was the rule in the U.S. So if you're going 60 miles an hour, you would want to keep 8 car lengths between you and the car in front of you, which is a long distance right there. But the whole idea is that at 60 miles an hour, which is roughly about 100 kilometers an hour, 62 miles an hour, up there. So you're looking at roughly 100 kilometers an hour. If this guy stopped all of a sudden, that there, you have time to stop before you hit the back of his car. And I don't know how many times you've seen people driving cars where they're like this, going 130 kilometers an hour down the expressway, and there's like maybe 6 inches between them, or 10 centimeters between them. If this car is stopped, then of course you have an accident, right? So, right there. So, but that's the ultrasonic sensor. The touch sensor actually measures the change in capacitance. They don't necessarily show that here, but we have electrical connections. We have a sheet, and we place an object, and we recognize. Again, this is an example of a fingerprint sensor right there. You know, my phone has got a little thing on the back here that if I put my finger on the back of this right here, it can read my fingerprint and tell whether or not I'm the authorized user of this phone. That's there. When I come into work, I'm supposed to put my fingerprint so that they know that I'm here. That's there. But again, we're looking at a very fine sheet and connections underneath there that we press slightly in order to make these connections right there. So that's a touch sensor right there. Pressure sensor right there. We have a substrate, and we're bending the substrate right here, pressure sensitive rubber. This actually is used, again, in scales or measuring pressure. It can be used in all kinds of applications. If we're picking up an object, we have to know how much pressure we're placing on the object to pick it up in a much better robot so that we don't break the object. So quite often we would place pressure sensors in the gripping hands, right there. So, right there. Pressure sensors can be used in all kinds of places, right there. And the last one here is a force sensor. This is a strain gauge. A strain gauge, I'm not going to go into much detail. And as you look at this equation, you can see why I'm not going to go into this equation, right there. But this measures the change in inductance as we move this thing, bend this thing around right there. And so we have multiple forces and movement that goes into it. And I'm just going to fly through these. I have a little bit of time, but actuators, these are the 3 types again. They talk about the advanced, but just a quick review, because right there. And stepper motors I didn't talk much about before, but the stepper motor has, in this particular case, 6 poles, 6 pairs, or 3 pairs, excuse me. This one's got 4 poles, so it's 4 magnets. 1, 2, 3, 4. Yeah, this has got 4 magnets right there. One forms a magnet with 5, 2 right there. But the whole idea is that we can send a sequence of pulses to it right there, and we can tell it to go to here. So if we're in position 1, we magnetize these 2, then it's going to pull it around. Then we magnetize this set and pulls it in that direction. So we go through and alternate which set of poles, which magnets are going to pull this thing around right there. So, and this is actually a fairly poor example, because this here is a north-south pole, north-south, north-south. These are they're alternating right there, north-south. It's north, south, north, south, right there. So the whole idea is that we can make this a north, and that pushes it in this direction right there. We make this a south, So we can vary the polarity of the electromagnets in order to rotate the center magnets. And this is called they call it a stepper motor because we can move it a certain number of steps that they're controlling that there. And with a computer, we can keep track where we're at. Stepper motors are popular in a lot of applications, right there. I used to have one with the satellite dish to keep track where your satellite is. They're used in a number of robotic applications, but the servos have taken over at the small end. We've already talked about the servo. Right. So this is just showing the sequence that they're showing phase C is energized right here, and they're not showing the phase A is energized right there. So phase A, B, C, they're showing it right there. This is actually A, B, C, D if you go around this way, or A, B, C, D in this direction right there. So what it's doing is it's energizing it it's going counterclockwise. So it's going phase A to phase B. It looks like it's going B, C, D, A. That looks counterclockwise right there. So the energization, but I'm not getting. I had negative torque motors. The linear stepper motor again. The whole idea is you got the magnet and you just pull it along right there. And I think that I'm going to stop here at this point. We've already talked about servos right there. Pneumatic actuators. This shows a picture of what one looks like. Again, we're just moving this. This is the valve that allows air to flow through it. Hydraulics go the same way. Ultrasonic. Yeah, the first part of this, don't worry too much about right there. Ultrasonic. That's there. Only worry from this set of slides, only worry about the sensors. The motor discussion today, from these slides, don't worry about it. Right there. Only worry about up to the pressure sensor. And again, it's more definitions of where it's going to be used. Because if you look at I didn't post it. Okay. And I'm not going to look for it, but if you look at the questions, you'll see that I don't get into details on the sensors and how they work. It's what they're used for, when they're used, right there. So this actually gets into a little bit more detail. I think I'm going to kind of finish. This is my end of discussion on robotics. We're going to start after the midterm. We'll start up with the for the rest of this course. We're going to be looking at PLCs and industrial automation. Right there. So, any questions? Be sure you tell everyone to be here on Thursday. I haven't taken attendance very well. I don't really worry about attendance, but I will probably find out Thursday to a great detail who's not here, even if they've seen what the test looks like and talk to you, look at your notes. You can almost tell who's not showing up to class because they don't prepare that there. So usually the exams tell me who's been here and who's not. When I grade final exams and I've got the class average up in the 80s and I got 4 or 5 people down around 10 and 12 on the final exam, I know that they hadn't shown up to class much. Right there, it's fairly easy to tell who's not here. That there. So. And I also come from the school of thought, and this is just kind of a side note, that I don't put a lot of weight on grades or even that they're the only place that I really get kind of particular is like your final year paper. Yeah, out there. And since I'm retired, I can kind of give my philosophy. I want to see something that works. I want to see something that you've actually done, and some real engineering work. That I don't want to see. Yeah, and so much is done with simulations in this program, but I want to see that you actually have thought the design process through and thought there. And there, when I look at assessing a program in particular, I want to know what the graduates have done when they've left the university. What type of jobs did they do and how well they succeeded? Same thing when I look at an engineer is what can they do? And I got a lot of stares on people back when I made the comment a number of years back when I first started here, that that I said PhDs don't necessarily impress me, because I've seen too many PhDs that can't produce any work, can't design anything. They can research and regurgitate publications in order to get through a dissertation, but as engineers, they're completely worthless. And I've also known some PhDs that have made me look like I was stupid too. I should that although that's not hard to do on some days, but I've had some PhDs that are brilliant out there, but they're people. They're just like, there's a spectrum of PhDs, and the ability to get a PhD is not a direct correlation to one's abilities or intelligence. Just because someone's got doctorate in front of their name or professor in front of their name, like myself, and when it comes to title, I am a professor emeritus from Purdue University. So I mean, I've got a title that's fairly impressive. I'm not talking about the UNIKL title. I'm talking about my lifetime title from Purdue, which is a top 10 engineering school, and I've spent 30 years there. And titles don't impress me. I don't throw that title around. I mention it, I've got it just simply because it's part of the discussion But I've fired PhDs in my career. And I've been looked at as, says, you fired somebody with a PhD? I said, sure I have. And I've also seen PhDs walk into a classroom that they're without any rich experience, but a PhD, feel that they walk a foot above the rest of the class because of their PhDs. And I've seen this done with people with only bachelor's degrees, with associate professor, or assistant professor in front of their name, or adjunct professor or something like that. But they treated the class like the class was stupid, and they were teaching a course at night filled with students that were working full-time for industry as technicians or associate engineers, and these students actually knew things much better than the instructor And one particular faculty member we hired, and I was in the committee that hired her, so I feel partly responsible, was a young woman that came right out of a PhD program. She had some industrial experience on her resume, looked pretty good, talked a pretty good game during the interview, got in front of a class in her area that her dissertation was in. And there were several members of the class that worked for Raytheon at the time in that area. So these were people that were working on leading edge technology for a military contractor. They knew that material inside and out. I mean, they really understood it. And she started talking textbook bullcrap. And when I say textbook bullcrap, I'm talking about stuff that's written in textbooks that will never work if you actually did it in the real world. And there's a lot of that out there. I shouldn't pick on textbooks. I've put together a draft for one, and I decided it wasn't worth the time. There's too many textbooks in that area already, so and you don't make any money off of textbooks anyway. So, and I was already tenured, so I didn't need to get the publication. But a lot of textbooks are written by professional faculty that have never worked in industry. And they're written with the idea of teaching that there. And when you go out and you actually try to apply this stuff, it doesn't work. Now, I really haven't taught you much detail on robotics because I don't want to go into a lot of textbook garbage that you're not going to remember. It's not important anyway. I want to get across the concepts and the ethical issues and the social ethics more than I do the textbook logo right there. Now, going back to that slide that we had up here, right there. I mean, I could go through this and I could give you a problem where I put a certain force in here and I'm going to ask you to calculate all these various forces right there. In other words, I'll tell you, I give you this matrix and I give you say there's a particular force, you have to calculate what W1 through W8 is, then you have to tell me what these various forces are, and you could spend a lot of time in MATLAB putting these numbers in, right? And heaven forbid if you had to do it by hand. That's or I could get into, so these aren't very good slides that there, but the modeling that there, we could get into this right here as we're writing the model of a particular force right there. This is, by the way, this is the stuff that's in the textbook that's required, specified for this class. This is the kind of stuff that's in that right there. So that's what I mean by textbook logo. But getting back to what I was trying to say earlier is that when you graduate, you're going to get a degree, right? Inshallah, you all graduate, and that's like Southern, living in Indiana, y'all coming out there. I'm not from the South originally, but everyone will get a college degree, and you're going to go for job interviews. And of course, when you go for job interviews, the person interviewing you is going to evaluate you in part on the way you dress, the way you talk, whether or not you've had a haircut that day. Not the ladies; they won't check you for it, see whether you had a recent haircut. But obviously, they're going to look at whether or not you're wearing clean clothes and whether they're professional attire. So your looks are going to come into play. You hate to discuss that. The way you talk will come into play. Do you talk with confidence? Do you talk loudly and clearly where they can understand you? One of the problems that I've ran across, and this is not, I don't want to necessarily make this to be a racist comment or sexist, but a lot of Malay women tend to mumble when they talk to men. Again, it's part of that modesty that they're, but when you're in a job interview, that's not the time to be modest. You're selling yourself. So you've got to be forward. Your technical skills are not necessarily going to show up so much in the interview. They may ask you a few questions about your final year paper. They may ask you some technical questions. But what they're looking for, more than anything else, is your communication skills. It's the soft skills that are going to get you that job. Once you're employed, your technical skills will come into play to a degree. But one of the places where modern education has fallen short, and I can say this after 34 years in the education field, is that the university's number one job is not to teach you a set of skills. I can teach you all those linear differential equations. I can teach you all the 8x8 matrices all I want, how to solve them. That is not going to help you in your career. The number one thing that you need to walk out of the university knowing is how to learn, how to teach yourself, how to look at a set of slides and some questions I didn't really give you the answers for, and figure out how to answer those questions right there. On a test, you're going to be given questions you don't know the answer for. How well do you think in order to come up with the answer, the thinking process? And that's where universities are falling short today. And I'll pick on my university back in the U.S. We have kind of, university, there's been so much pressure from industries to tell us to be sure they know how to do this, and we forget to teach people how to actually go out and go into the library and learn. Professor Google has become too easy for people to just look up answers. Back in the old days, we used to have to spend hours digging through books and understanding things. And that's where the next generation of technology comes from, is that ability to go beyond what you can do by teaching yourself, understand the basics, and then the ability to think. And we don't do enough of that at the universities. And I know I don't do enough of that in this class. I don't force you to think too much. I'm trying a little bit, when I get into social ethics. But is what generates the leaders of the next generation. Is the ones that can kind of think beyond what you're currently doing. And what we're teaching here is, what is today's technology? Memorize it and regurgitate it back. Memorize it and regurgitate it back. Right there. And that doesn't necessarily lend itself well to being a great leader. And I think almost all your classes do that, right? That there. I know Dr. Tyrell has a class on society engineers, but I think that's more on the ethics side where you fit into. And ethics do play into it. Right there. I've mentioned that there. So as I'm kind of winding down my career a little bit there, I'm just kind of giving my viewpoints in your sounding board that if you walk out of this class knowing nothing about robotics, but you start thinking about how to think and how to do research and how to make that there, you've learned something probably more valuable. Now, if you end up in a position where you need to specify robots and you need to understand the basics, but you're not going to understand well enough to design that robot, I can't. That's it. So it's one of those things you have to look at right there. And I'm kind of rambling, so I'm going to go ahead and shut down where's my recording? Right there.